All right, so we'll start. Good morning. Okay, so sorry, I've been quite sick this week, so I will try to do my best to speak as best as I can. I will only show one screen today because I will use the Blackboard a lot. So if that's fine with you, I will use this one. And yeah, I should try to turn this one off, but okay. All right. Okay, so the the goal of today will be to build and train our first neural network together. And so we'll try to build an architecture of a neural network from first principles. So we'll start with a very short history of neural networks, and I will give you one example, the case of the multi-layer perceptron, and then we'll try to see how we can actually build or derive this architecture, this neural network, starting from first linear discriminant analysis, then we'll generalize that to logistic regression, which you should remember from machine learning, and then we'll use this logistic regression model to build a layer, and then from layers we'll build neural networks. Okay? And once we'll have these architectures, I will show you a bit the kind of functions you can represent with these architectures, and then we'll see how we can actually train them, or how we can actually optimize their parameters to achieve or to solve some supervised learning problem. And finally, I will conclude today with the problem of vanishing gradients and tell you about one possible way to fix this problem, which is related also to the architecture of the multi-layer perceptron. Okay? So that's the menu for today. All right, so we'll first start with neural networks. So neural networks, they are not new. If you go back into the history of AI, the very first neural network was proposed already in the 40s. And in this slide, what you see is a diagram describing the Mark I perceptron by Frank Rosenblatt in the 60s, the late 50s, beginning of the 60s, which is really one, I would say, one of the earliest instances of a full neural network. And what you see there is actually very close to what you see in modern neural networks. So this neural network was used already at the time to process images and to classify them in the 60s. And so you see three parts mainly. This first part is like a mechanical retina or an electrical retina full with photoreceptors. Okay, so it was just put in front of an image, and then depending on the light hitting the sensors, some of these units were then firing on, so producing some electrical intensity as output. And then these retinas, you see, they are connected through all these wires to other units, which were called association units. And in this diagram, what you see is that these connections from the sensory units to the association units are made of a network of random connections. And the principle was that each one of these units, association units, would be firing depending on the detection of a pattern in the sensory units connected to each of them. Okay? And so, for example, if, I don't know, these three first units are connected to these ones, and if all of them together are on, then this association unit also turns on. Otherwise, it turns off. Okay? And then the idea of the architecture is to repeat that in a hierarchy. So you compose these associations in a hierarchy of patterns. And so you would have now a second layer of units, which in this case were called response units, which are themselves connected not to the sensory units, but to the association units, the previous units. And so now you would have these units, they would turn on themselves if, for example, they are if you have a pattern of association units turning on as well. Okay, and in this way you can start going from very raw data at the sensor level up to higher and higher patterns that you can start detecting using this kind of architectures. And so this neural network was not actually implemented in software, it was implemented in hardware. And so this is the machine which was implementing the connections between the sensory units and the association units. And so these are these random connections, and I would presume they are kind random when you look at them. You see there like the interface of the machine. This is like an image in front of a camera, and then you see there the corresponding sensory units being turned on or off. And so in this case, you see that all these units, they are on because they correspond also to the white part of the image. Okay? And so it might be surprising, but already at the time you could use this system to not only classify images, but also to learn to classify images. Okay, so you would have the computer, you could actually train the machine to recognize faces or men and women by just presenting to the machine an image together with the correct label, and then the system would be able to train itself to modify the configuration in a sense to solve the task. So I can show you this.
In the 1950s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
Okay, so that recipe is exactly what we'll see today. And so even though it was already used back in the 60s, it's only now, or it's been 15 years or so, that we are back and trying to build neural networks and we are able to train them. But just to tell you that this is not new, okay? The recipe itself is not new. Many things have changed, but fundamentally, what they could do in the 60s is what we'll try to do today, okay? Okay, so one of the main ideas that you should remember already from this lecture is this idea of composition, okay? The fact that we start from that we'll have simple units that are connected to one another, and that would basically produce an output, a positive output, upon the detection of some kind of pattern. Okay? And then the idea will be to compose these units together into layers, and then to compose these layers in series into entire neural network. But fundamentally, each one of these units, so in the case of the Mark I perceptron is one of these units, like the association or the response units, you can really view them as some kind of binary classifier, a very simple and simplistic binary classifier that will compute, in this case, a linear combination of its inputs, and will apply a step function to the results. So mathematically, in the modern sense, we would have each unit acting as a simple classifier, and each unit could be, for example, implemented this way. So each unit would be some function f that takes as input some vector of p elements, okay, real values. And then what we would do is that we would compute a linear compositions of these elements. So you would do a weighted sums of the values inside a vector, so the value xi, and you would have a weighted sum which would be dependent on some weights wi. So you would compute this sum of products together with an offset b, and then you just check whether or not this quantity is above 0, in which case you return, or the function returns 1, otherwise it returns 0. Okay? Very simple. All right, so this already can be rewritten, and so the next few slides will appear very simple, but it's also a way for me to just introduce the notations I will use today and throughout the course. So this classification rule that you saw in the previous slides can also be rewritten in this way. I can rewrite it as f of x being equal to the sign of this quantity, which is this weighted sum of the elements of my input vector. Okay? And I want to rewrite it like this because in this way I will call this function sign a nonlinear activation function. That's the term we use in deep learning. Okay? And this function itself would be implemented simply like this. So it's a function that returns 1 if its input is positive, otherwise returns 0. Okay? So let me use this. Okay, and so the sign function looks like this. Okay, even though it takes only 2 values, that's something you can represent. Okay, so it's just equal to 1 for all positive values, equal to 0 otherwise. Okay, so nothing complicated so far. But I can use that very simple model to also tell you about this concept of a graph of computation or a computational graph. And basically, if we were to compute this quantity on a computer, how would we do that? Or if I were giving you this quantity to compute, given known values of w, x, and b, how would you compute that? So supposedly, the thing you would do would be simply to compute each elementary part of this expression, and then you would compose these elementary elements together, depending on the operations that we need to do to compute or evaluate this entire expression. Okay? So to compute this, to compute the sign of this quantity, we first need to compute this quantity, the inside, so the input value of the sign function. But this is itself an expression which is composed of several primitives. It has a sum over several elements, and each term of the sum is composed of an addition together with a product of 2 values. Okay? So I can rewrite this in this way, where what you see, so you see circles and squares. The circles, they represent variables, quantities that are either given or are being computed. Okay? So we have the inputs, x0, x1, and x2, if we assume vectors of 3 elements, together with w0, w1, w2, okay, which are parameters, but which are also inputs. You have b, this offset, and then you see h, which will be the variable corresponding to the output of the computation. Okay? And what I'm just saying is that I'm just now organizing all these variables together, and they would be connected to squares if you combine them through an operation, through an instruction. Okay, so in this case, I would assume, for example, that I have a primitive operation to multiply 2 quantities, to multiply 2 scalars, for example. So x0 times w0, and I can reuse that also to compute the second term x1 times w1 and the third term x2 times w2. Okay? Then I can also assume that in my programming language, let's say I have access to a primitive to sum quantities. Okay? In this case, that would be the add operation, which would add together these 3 values that we have computed before, together with the b parameter. Okay? And finally, add itself now would return another quantity, in this case a scalar, which would be fed as input to the sine function, which I can also assume to have access to directly in my library of primitives, and finally would produce the output h. Okay? You will see later on why this concept of graph of computation is actually very useful. What we can do also is that usually in deep learning will not work at the level of scalar elements. We'll work instead with matrices, vectors, and more generally with tensors. And so I can rewrite this perceptron model in terms of tensor operations. And the way I would rewrite it would be simply by rewriting this sum, this weighted sum, as a dot product between two vectors. Okay? So in terms of tensor operations, I can rewrite this as W transpose times X, where now W and X are both vector, plus some scalar B. Okay? And if then I assume that I can do in my programming language operations, primitive operations directly at the level of vectors, matrices, or tensors, then that means I can also rewrite the corresponding graph of computation directly at that level. And in this case, I could simplify my diagram in this way, in which now you see that we have a much simpler diagram. So now we have only one node for X, because X has become a vector instead of being three scalars, the same for W. B is still the same and H is still the same. And then we have replaced the products between the elements of X and W, and the sum, we just a dot product. Then we add, same operation as before, we take the sign, and then we produce the output. Okay? All right. So remember this model, because you will see that what we'll arrive to in just a few slides will be very close to that. Okay. Now the question I could ask you is, okay, let's say you want to use this model to classify or to solve a supervised learning task. So you would like to fit W and B, okay, such that you produce output H, which are good in the sense, for example, of a classification loss or in the sense of a regression loss. Okay? How would you actually do that? How would you find good parameters, good parameter values for W and B? Yes? Mm-hmm. Okay, so let's say we want to do regression to make things simple. Okay, so we want H to fit like the same line as we had last week with a few dots. We could use as a loss, like the squared error. Okay, and then what? Now that you have the loss, how do you actually find the values of W and B? Okay, so if you do gradient descent, okay, think about what would happen as you fiddle with W and B on the output of the function. Since the function is basically acting like this, because it's the result of the sign, if you change only slightly W or B, very likely you will stay. So either you are currently there and you will stay there, or you are currently there and you will stay there. So that means the gradient of W with respect to the output, the gradient of the output with respect to W is 0, and will be 0 everywhere. So how do you use gradient descent if your gradients are 0 everywhere? That will not work. Okay? So already with this model, we are faced with a very big obstacle. We can't use just numerical optimization algorithms to find the good values of W and B. Because, for example, if you use gradient-based optimization algorithms, these gradients will be 0 everywhere. So we'll be stuck. Okay, so to give you the solution, we'll find a solution, but we'll go step by step. And so we'll start with the model of linear discriminant analysis. Okay, so we'll assume a regular supervised learning problem where we have a data set of pairs, inputs and outputs that are drawn from some joint distribution, okay, which we know exists, but we don't have a direct access to except for the realizations we have in the training set. We'll assume that these are vectors, okay, and we'll assume that the y values, they are binary. Okay, so we have a binary classification problem. We either want to classify X to be in the first or the second class. Okay? And we'll assume basically that we have something like this. So if this is the X space, we have maybe the X values for the first class being all gathered together like this, for 0. And for, so that would be X given Y equals 0, and here you would have X given Y equal 1. Okay? So that's the setting we would have to start with something easy. Okay? And then in LDA, linear discriminant analysis, we'll be making a strong assumption. So we'll be defining directly the conditional distribution of the data X given the class Y. Okay? And the assumption that we are making in LDA is to say, okay, this blob of data is Gaussian, this other blob of data is Gaussian, and we'll say that these two Gaussian distributions, they share the same variance. The only thing that changed from one to the other is the position of their mean. Okay? Okay, so we'll say this is Gaussian of mean mu y and covariance matrix sigma. Okay? So that means we'll have a vector mu for y equal to 0 and another for 1 equal to, when y is equal to 1, but the covariance matrix will be the same regardless of the value of y. Okay? Okay, so if this is our model and we want to solve our classification problem, basically what we want then to do is, for example, to estimate or compute the conditional distribution of y, and let's say, for example, the conditional, so the density or the probability of y being equal to 1 given x, okay, given some input, what is the probability of the positive class. How would you do that given this assumption? How would you derive this conditional given this other conditional? Okay, usually when I ask a question, there will be two answers, either the Bayes rule or maximum likelihood estimation. So which one of the two? Yes? What would you do with the Bayes rule in this case? No. Yes. Okay, so with the Bayes rule, you can rewrite this in this way. And for the specific value of the positive class. Okay, and why is this useful? Well, because the joint, you can rewrite it as the product of a prior and the likelihood. So P of x given y1 times the prior probability of y1 over px. Okay, so far? Then what I will do is that I will rewrite this. So I will rewrite this marginal by making the y value reappear. Okay. So I have P the same as before. But the marginal probability of x is what? Is the conditional probability of x given the negative class times the prior probability of that class, or the conditional probability of y in the other case when y is equal to 1 times the prior probability of y1. So in this expression, what I will do is that I will divide both now the numerator and the denominator by this quantity, the quantity at the numerator. And in this way, I arrive to this expression. So far, do you all agree? Okay, and now I will introduce a function that I will call sigma, which I will define as 1 over 1 plus the exponential of minus x. Okay. I can do that. Yes? Okay, I'll try. But everything I'm writing is also in the slides. Huh? Okay, so if I have this function now, I can rewrite this, this quantity as directly sigma of log of P plus okay. Okay, why is this helpful? Well, you will see very soon. So this log of this ratio of marginal probability of the y values is basically a constant. Okay, we can come with a prior on the probability of each class. Okay, and this will simplify. So we could say, for example, that both classes are equally likely. Okay, in which case you would have a log ratio of 50% over 50%. That's 1, and the log of 1 is 0. Okay, or you could assume another distribution for the two classes. Okay, but that's an assumption you would come with. And at the end, you would have this term, okay, which is just a constant. Okay, so I will rewrite this as a constant, A, and I will rewrite my expression as the difference of the logs minus log okay. Okay, so how can we go further now? Well, we can now use our assumption about how the data is distributed. So we assume that Px given y was a Gaussian. Okay, so that means this log of this conditional are just the log of the normal distribution, or the density of the log of the density of the normal distribution. Okay. So I can assume that, yeah, we'll do it like this. So after simplification, what we would arrive to for the first log density is minus 1/2 of x minus mu1 for the positive class, transpose times the covariance matrix times x minus mu1. Okay. Then minus the other log density, which becomes a plus. And now it's the difference to mu0 plus A. Okay, and now if you shuffle everything around to isolate everything related to x, and then you put everything else together, what you should arrive to is mu1 minus mu0 transposed. Oops, sorry, there is minus 1 there. Times the inverse of the covariance matrix times x plus 1/2 of mu0 transposed times the inverse of the covariance mu0 minus mu1 transposed inverse mu1 plus A. Okay, and now what I will say is that this quantity actually is just a vector, and I will call this vector W transposed, and this quantity is actually just a scalar, which I will call B. Okay, and so in this case we arrive finally to something very, very simple, where we do the dot product of W together with x plus b. Yes. Mu is the mean vector of one of the two distributions, the two normal distributions. These are parameters of the normal distributions we assume. No, the mean of x. Okay, it's a distribution over x conditionally on the class. Okay, it's this. So if I'm taking this one, we are just assuming these red points, they are Gaussian distributed. Okay, with a mean here, which I will denote as mu1. Okay, and similarly for the other class, we would have another Gaussian distribution with a mean here, which I will call mu0. Okay? Mm-hmm. Yes. Of the mean of the distribution, simply. Okay, so what I'm now saying is that this model is actually very close to this one. Why? Because actually, if we were to plot this sigma function, so before we had something like this for the sine activation function. Okay. For the sigmoid activation function, we have something like this. So sigma is, yeah, sorry, I'm not sure I've introduced the name of that function, but it's called the sigmoid activation function. And it's basically the same kind of Heaviside function, but it's like a softened version of it. Okay, where we don't get a rapid change going from 0 to 1 or from 1 to 0, but we get a smooth change from one regime to the other. Okay? All right. So, but how do we fit the parameters of this model now? How do we fit the parameters? So we need, in order to evaluate this quantity, we need W and B. How do we find them? Yes. Yes, you could do that. But actually, if you were doing that, you would violate our assumptions. So do we need actually to do anything smart in this case? Not really, because to know W, the only thing I need to know are mu1, mu0, and sigma. Okay, so the only thing I would need to do to fit this model, in a sense, would be to have an estimate of mu0, an estimate of mu1, and an estimate of the covariance matrix. And I can just do that using the training set. Okay, so using your training set from above, you can just isolate everything from the first class, then you compute the mean vector, that gives you mu1, you do the same for the negative class, that gives you mu0, and then you can also use all your data points to compute an estimate of the covariance matrix. And then you plug these three quantities in this expression, you obtain W, and you, sorry, you also plug these quantities there, and there, and you make an assumption about how the classes are distributed. That gives you B, and then you are good to go to evaluate this for any X. All right? So if you do this, you would get something like this, for example. So in this case, we have a data set of points, the blues, the blue points and the red points. And if we do this linear discriminant analysis, we would fit a mean and a second mean. These correspond to the two big black dots. The corresponding Gaussian distribution would be represented by the ellipses. You see there that the ellipses have the same shape. Why? Yeah, because we make because that's an assumption that we make. We assume that the covariance matrix is the same. Okay, and under these assumptions, then I can derive this model, and once I have this model, I can classify any point. Okay, and so everything to the left of the bar of this black line would be classified from the red class, and everything to the right of that line would be classified to the blue class. Okay, and you see that of course this model is not perfect. You have, for example, in the training set, points that are actually red but which you classify as blue, and vice versa. You have blue points which you classify actually, which are actually blue but which you classify as red. Okay, but that's a very simple and naive model. You cannot expect it to work very well, of course. If we had, for example, this setting, here we would have a much better result in a sense, because in this case the two blobs are clearly of the same covariance. They do not overlap, and so in this case you would not be making any wrong predictions. What is also interesting to look at is what would happen if our assumptions are obviously wrong. So for example, if the two conditional distributions do not share the same covariance, like in this case, obviously, the model would not know about that, so it would still make these strong assumptions that these two blobs, they have the same covariance matrix. In this case, we would get something like this, which is making correct predictions for red and for a good part of also actually it's also making correct predictions for all the blue points in this case. But you see clearly that the same model would associate also very low density to blue points, which are actually very likely. Okay, so this is not in this case a good model. Okay, and as I said already, this sigmoid function, 1 over 1 plus the exponential of minus its argument, looks something like this. So it's almost like if this LDA model was some kind of perceptron in which we have relaxed, in a sense, this sign activation function with a smooth version of it. Okay? The corresponding graph of computation would be very similar as before, almost identical. The only change would be this final operation, which, so in this diagram, we've replaced the sign activation function with the sigmoid activation function. Okay? So it may not look like something really important, but really, if you look at any modern neural networks, what you will see are computations of this kind almost everywhere. Okay, so you should really understand this first brick, okay, as like the basic element of a neural network. Do you have questions so far? Okay. Okay, now let's do the same, but without the assumptions. Okay, do you know about logistic regression? Anyone? No? One? So, contrary to what its name suggests, the logistic regression model is not a model to do regression, but to do classification. Okay, except that we would do regression on some internal quantities. But it's really a model, again, that we'll use to represent the conditional probability of the output given the input. Okay, and we'll assume, again, a classification problem. So when the output, in this case, is binary, and it's either positive or negative. Okay, and in the case of logistic regression, we assume that this conditional probability follows this expression. It's the sigmoid of W transpose times X plus B. So exactly the same as before, except that now we'll not say that W is the result of this difference of two means multiplied by the inverse of the covariance matrix. We just say this is a vector, and similarly for B, we just say it's a scalar. Okay, so we'll not be making any assumption about how the data X is distributed conditionally on the class. Okay, the only assumption we'll be making is on the conditional distribution of Y given X, but not in the other way around. Okay? Okay, so now we are back to the same question as before. If this is our model, then our model comes with parameters, the W and B. How do we actually find good values for W and B? So as I said, there are two possible answers, Bayes rule or maximum likelihood estimation. Okay, so we can do maximum likelihood estimation to retrieve or to do, identify values of W and B that would explain our data well. Okay, and so what we can solve is this optimization problem, in which we'll say that the optimal value of W and the optimal value of B are those given if we solve this maximum likelihood estimation problem, in which we'll just say that we want to consider the maximum over all the W's and B that will maximize the probability of our data set. Okay, so let's assume that our data set is D, conditionally on W and B. Okay? So D, just so that it's clear, is my set of pairs xi, yi. Okay? If I assume that my data is ID, I can rewrite this joint probability as a product of marginal probabilities over the elements of the set. Okay, and what I have is a big product over the element xi, yi in D of py taking the value yi given xi and given W and B. Okay? What is py given x? Py given x is simply our model, what we've assumed. Okay, so we'll just now be replacing this conditional probability by the expression of the model that we've assumed to start with. Okay? Okay, but we have two cases, either yi is positive or yi is negative. Okay? If it's positive, then the probability of the positive class is given by this expression, the sigmoid of this dot product of w and x plus b. Okay, but it might be that actually yi is not the positive class, it's the negative class. Okay, in which case what I would have had to use instead is the complement of this probability value. Okay, so 1 minus sigma of wt xi plus b. Okay, so it's one or the other. And one trick to select one or the other is just to say, we'll multiply these two quantities together, but we'll take this quantity to the power of the class, so yi or 1 minus yi. Okay, so if yi is 1, then this thing will simplify to only this term, because if it's equal to 1, then 1 minus 1 is 0. Okay, and if you take some value to 0, you get 1. And vice versa, if yi is 0, this becomes 1, and you only select this part. Okay, and now, if you try directly to maximize the product of probability values over a large training set, you will get numerical issues, because you will get something which tends to 0 very, very quickly. So what we do instead usually is to maximize the logarithm of the density, the logarithm of the likelihood, which can also be written as a minimization problem over the negative of the logarithm of the likelihood. Okay? So I'm rewriting this now as a minimization problem. Of minus the logarithm of this quantity. So we get the logarithm of a product, which becomes the sum. Well, in this case, yeah, I will do it like this. So the product over the element becomes the sum over the element of the data set. Okay. And now we have the logarithm of this expression. Okay, again, we have the logarithm of a product, which becomes the sum of a product, and we can also use the logarithm of a power to pull out these y values out. And so we have, at the end of the day, something like this. Minus 1 minus yi log. And this expression is what we call the it's basically a loss, okay? A loss between yi, the correct value, and our prediction, which in this case is, well, let me denote it like y at I, okay? And this particular expression for this loss is the cross-entropy loss. Okay, so this is something I like to insist on as also. You see that we arrive to a loss, okay? But if we have not started with a loss, okay, we arrive to a loss because we just make assumptions, generative assumptions, or assumptions about the distributions of the, in this case, the output given the input, and then everything else follows from just doing maximum likelihood estimation. Okay, and very importantly, you see that we do not arrive to the 0-1 loss. Okay, we arrive to the cross-entropy loss. Okay, and this loss, now we have to minimize it. And to do that, then we'll use numerical optimization algorithms. Okay? All right, so now that we have seen this logistic regression unit, and I will put it there because it's so important. What we'll do is that we'll compose this unit to build a neural network. Okay? Okay, so how can we do that? Well, the first thing you should realize is that in a sense, this one is a very, very simple neural network. Okay, and usually I will be making these kind of drawings in which I have rectangles which usually will represent vectors. Okay, so we would have, for example, some input x, okay, with p elements, and we'll map this vector onto a scalar through connections, okay, but these connections will simply be the w elements, okay, that are associated to each input value. Okay, and this would produce one single output, which would be f of x. Okay, which is defined as sigmoid of this w tx plus p. Okay, so in this diagram, these lines represent connections, which are the wi. Okay, and this element would be xi. Okay, the b there is not shown, but you could assume it's a hidden connection which arrive to this element. Okay, and the computation being made at this box is this dot product, this sum, and the sigmoid activation function. Okay. So this is the logistic regression unit. Now, how do we use that? How do we compose this unit to obtain neural networks? Well, the first thing we'll do is that instead of just considering one of these units, we'll consider several of them in parallel. Okay? So if you instantiate, I don't know, Q of these units, and then you concatenate all the outputs, what you obtain is not one single output, but Q outputs, which you can bundle all together into a vector of size Q. Okay? So this is what I will call a layer. So a layer is simply a parallel composition of logistic regression units. Okay? And so we'll have the same kind of expression as before, almost. But we'll replace the W vector by a W matrix, such that the dot product of a matrix with a vector will produce a vector. Okay. B will be upgraded similarly now from a scalar to a vector. Okay. So this quantity will produce a vector of size Q, and then we'll apply element-wise the sigmoid activation function to each element of this vector to produce another vector of size Q. Okay? And so if I was to draw this, I would have something like this. X. And now I'm mapping this to a vector, which I will call H. Okay. And each of these boxes is the result of one of these logistic regression units. Okay, so each box, for example, let's say this one, HJ, would be, okay, so we would have connections. Okay, and similarly, if you were to, I could show you this one, which would itself be connected to all the other elements. But what is important is that these connections, these weights, now they become specific to one of the units. Okay, if I, so these weights now, these correspond to the weights associated to the output J, and you have similarly P of them. Okay, but if I consider, for example, this one, then I would have other connections, okay, which are different, so they are distinct parameters from these ones. Okay, we also call this this model a fully connected layer, fully connected because we assume connections from all the inputs to all the outputs. Okay, so we have built layer as a parallel composition of these logistic regression units. And then in deep learning, what we do is that we build deep neural networks by composing now layers in series. Okay, so now what we'll do to obtain the first neural network from this course is to say this vector will now be used as input to another layer. Okay? And so I can now say that, for example, I would start from a first vector h0, which corresponds to the input. Then I would say that h1, the first layer, is something like this. So sigma of W transpose X, or rather h0 plus B. Okay. To make things clear, I will also associate each one of these two parameters, the W matrix and the B vector, to the first layer. Okay. So this is W1 and B1. And then I can say that, but actually this vector, I will use it as an input to a next layer, which will produce another vector, maybe of the same size or maybe of a different size. It's up to you. But it will be computed similarly as the sigmoid activation, the element-wise sigmoid activation of some matrix H1 matrix times vector multiplication plus B2. Okay, and you can repeat that for a certain number of layers. Like you can stack, let's say, L of them. And you would have that this is the result of WL transposed HL minus 1 plus BL. Okay? And so if I draw this model, what we have is something like this. Again, so we have the input vector, x. Then we map this to a first vector, a first layer, using a fully connected layer. So we connect everything to everything. So when I draw just these two lines, it means that I assume everything inside is fully connected. That's what it means. So here we have H1. And then we say, for example, H1 is connected, produce another vector, H2, using another layer. We could say maybe we map this to more values. That's up to us, H3. And then finally, maybe we map this back to maybe a single value if we have to predict just one single value. Okay. So this is the multi-layer perceptron. Okay. The main idea is to start from the logistic regression unit, this very simple classifier, to compose these units in parallel. If you do that, you get a layer, a fully connected layer. And when you compose these layers in series, when you stack them one after the other, you obtain a multi-layer perceptron. Okay, so far? Okay. Let's take a break then, and we'll resume in 15 minutes. Okay. So what have we seen so far? We have seen the multi-layer perceptron architecture, which you can see or understand as a composition of these logistic regression units in parallel and then in series. Okay? So I've given you so far a very descriptive set of slides where I'm telling you this is what they are, but I've not really told you why why we've designed these architectures in this way or in some other way. Okay? And maybe the first element we should start thinking about is the concept of a layer itself. So if we take a layer that produces some vector h by taking the nonlinear activation of some linear projection of its input, x, okay? And I'm omitting the b vector, it's not really important. Can any one of you tell me what does it do actually? What's the effect of doing this multiplication, of multiplying x with this matrix and then passing this through a nonlinear activation function like the sigmoid activation? How do you understand basically what's going on? Yes? Except that this is a vector already, so what do you mean? Yeah. So this is a vector. The whole output is a vector. Okay, but what you're describing is at the level of the elements of inside the vector? Okay. Yes? Okay, so that's an interesting idea. What we are doing is that we are basically projecting the data into another space where supposedly it's simpler to solve the task. Okay, but where do you see that in that equation? Or if, more simply, I'm just talking about this. Okay, what's the effect of multiplying a vector by a matrix? It's the rotation. Anyone can help. Yeah, but it can do a rotation. It can rotate the vector. Yes. What transformation? Yes, but still, you cannot do any kind of transformation. It's a linear operation. Okay, so you cannot transform arbitrarily the data by multiplying x with the matrix. So what kind of transformation do you obtain when you multiply a vector with a matrix? Yes. Yes, so exactly. So what can happen is that these vectors, they can rotate. They can also reflect. Okay, you can have the mirror. You flip the direction. And also you can make them smaller or larger. Okay? Where do you see that, actually? So you can see that from the SVD decomposition, the singular value decomposition of the matrix W. Okay? So if you remember that by doing SVD, this can be rewritten as U, then some sigma, and then V transposed, and then you let me just forget about this. Okay. When you will be multiplying x with this, you will be rotating and reflecting the data. Then when we multiply further by this matrix, which is just diagonal, okay, you fill with the singular values, you will either stretch or squeeze the vectors, and then you will again rotate or flip the resulting vectors. Okay, so intuitively, really, how you should understand a linear operator is just rotations and then stretching. And so to give you like a bit of intuition, let's say we start with this bunch of points in 2D. So now I have a matrix filled with vectors of size 2, okay, which I show there with this scatter plot. And then what I will do is that I will just apply random projections. So I will create randomly a W matrix and just look at the kind of results, the kind of projection we obtain. Okay, so I'm just repeating 5 times this piece of code. I generate a random matrix. I multiply X with W. I compute the singular value decomposition, and I will use that also to show the axis and how the axis transform. Okay, so this is the initial data, and a first random projection would be like this, in which you see that we have squeezed the data in one direction, but stretched in the other. Okay, and you can see that being reflected also in the singular values. We have a value larger than 1, so we have stretched along one axis, and we have squeezed because we have value smaller than 1 in the other. Okay. This is another random projection. In this case, you also see the flipping. This is yet another, and so on and so forth. Okay? So when you multiply a vector with a matrix, this is what you should picture in your mind. Okay, the same. So here you see I've just used the at operator, which you can use directly on NumPy or torch tensors in this case. When you will be implementing neural networks in PyTorch, usually you will write things in this way by first specifying an architecture. And in the case of multilayer perceptrons, these are just so-called sequential architectures where you just have a sequence of layers. And so I can write the same linear projection as a very simple neural network made of one single layer, which is just a linear layer in this case. That goes from 2 inputs and produce 2 outputs without bias, without this B offset. And you see that indeed, if you instantiate randomly a neural network of this kind, you then make a forward pass, so you evaluate the output of the neural network at X, you obtain a random projection of that input, a random linear projection of that input. Okay? Now, what happens then when we add this nonlinear activation function? Okay, so in 1D, this is how it looks. We've already looked at this plot, but you can generalize that to n dimensions. So, for example, in 2D, if we start from this data and then project these vectors, or make this vector pass through the sigmoid activation function, okay, we'll apply it to each output, each element of the output vector. Okay, so if we start with this, we do a random linear projection, then we pass each element through a nonlinear activation function, we would get something like this. Okay, and now you see that it's no longer a nice blob like this, but rather we get this something close to the side of a square, okay, which is expected because the values that the sigmoid can take. So the sigmoid is something like this. Okay, so for this whole range of values will be in the positive saturating regime of the sigmoid, so you will get 1. And for the for this other range of values will be in the other saturation regime of the sigmoid function, so we'll get 0. And then it's only when we are in this small range that we may have values in between 0 and 1. Okay? So this is what you see there. And you can play with how much the data is being pushed to the border simply by amplifying or not the value of the input to the sigmoid. So here you see that I multiply with S. If I increase S, I will be pushing further and further the values into the saturation regime until I obtain something like this. Okay? Okay, now that we have this, we can start thinking about or start just exploring what would happen when we start stacking these layers of linear projection, sigmoid, linear projection, sigmoid, and so on and so forth, exactly as what we would do in a multi-layer perceptron. Okay, so if I consider this neural network here, okay, which I define as a stack of 2 layers. First, a linear layer, okay, of the same kind as before. I'm starting from 2 inputs, but then I'm mapping this quantity to a certain number n hidden of values, in which case, in this case, I would have set n hidden to 10. So I'm going from 2 to 10 values. Then I apply the sigmoid activation function, and then I stack another next layer, which would be also linear, but now would be going from n hidden back to 2 values. Okay? And I will be repeating this 5 times for 5 randomly initialized neural networks. Okay? And each time I would be plotting the resulting output. So this is the input, as before. And if we pass it through a 2 hidden layer MLP, we get something like this. Okay, what do you observe? I can produce more if you want. So before, when we were only considering linear projections, we are only flipping and rotating the data, or maybe also stretching the data or squeezing the data. Do you see the same kind of transformation in these projections? Okay, so remember these pictures. I will only change one line. I will remove the activation. Do they look the same as before? Okay, so tell me. Yeah. 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 What do you mean it looks linear? What do you mean when you say this looks linear? It looks like a blob to me, not like a line. I don't know. But think about the kind of transformations we are making. Are we just rotating, flipping, and stretching? Okay, if it's not obvious, this one, then I don't know. But then let's consider this neural network instead, where I will be stacking now more than 2 layers. So 1, 2, 3, 4, and 5. So does it look linear? That makes sense. No? Yeah? Yes, that's the main difference. We are bending the space now, which you can't do with linear operations. Okay? So we can points that were originally close to one another, if you just do linear transformation, they will remain close or far up to the linear transformation after in the projection space. Okay? But if you do a nonlinear transformation, regions that may have been close or vice versa, far away in the input space, you may even be able to map them or to put them close or even on the same output region in the output space. Okay? And that's what you obtain by just adding this nonlinear activation function. So if basically if you remove them, nothing works. Okay? Okay, we'll go back to this later on when we'll be trying to actually learn one of these MLP. Okay. One last thing before moving on. Something I've not told you really about yet is how do we design the output layer? How do we design this very last layer? Because supposedly it looks like it should be very dependent on the task that we are trying to solve. Okay, if we want to solve a classification problem or we want to produce vectors as output, it seems that we should make sure the output is designed properly to achieve this goal. Okay, so there are several cases, but the three main ones are there on the slides. So if you want to solve a binary classification problem, then the only thing that you need to do is to set only one element for the output layer. Okay, so you dimension the projection such that the output dimension is equal to 1. Okay, so we will say that we will set the width of the last layer to be equal to 1, and we will use a sigmoid activation function at the output. Why will we be doing that? Because if we do that, then we know we can use this numerical value as a probability value. Okay, because by construction, this numerical value will be guaranteed to be a number between 0 and 1. Okay, which is what we require if we want to use that as a probability. If we are doing multi-class classification, let's say we have images which we want to classify among 10 classes, then we need more than just one number as output. And the way we would be doing that would be by producing, instead as output, a vector where the size of this vector is the number of classes in your problem. Okay? So in this case, you would have, let's say, some vector HL minus 1, which you map to a vector with a linear layer, to a vector HL of size C, if we have C possible classes. Okay? But if we do just that with a linear layer, then we obtain a vector which can take any value, any real value. And these values, they cannot be interpreted as probability values, because we can have negative numbers, for example. Okay? So the trick to transform this vector into a vector that we can then interpret as a vector of probability estimates, so a vector of probabilities for each class. So we'll be feeding this vector into another function, which we call a softmax, which is another kind of activation function, which will produce a vector, let me call it y, of the same size, but now this element, so we'll get a vector of C elements, but now we'll be able to interpret this as probability values. Okay, and by construction, we'll have that this vector contains probability values. Each element can be interpreted as a probability value. So each element is in between 0 and 1. And when we sum all these probability values, we get 1. Okay, and so, for example, this quantity would be something that then we can interpret as P of y C for the class I given X. Okay? And what's going on inside this activation function, inside this softmax? Well, we need to fulfill the true properties for the vectors to be interpreted as probability estimates. We need positive quantities. And so what we'll be doing is that we'll just exponentiate the values. We'll pass these values through a function which only produces positive values. And then we'll normalize the elements of this vector. Okay? So this is exactly what you see there. We take so if Z corresponds to this vector there, okay, the Zi corresponds to the element of this vector. We take the exponential of each element. Now we get positive values, and then we normalize. We just sum that gives us a normalization constant, which we use to renormalize or to normalize each component in the output. Okay, and then by construction, now we'll have a vector for which all the values are positive, and if we sum them to 1, because they are normalized, then we get 1. Okay? Make sense? And finally, if we want to solve a regression problem, then that's the simplest case. We can just do something like this, where the previous layer is only a linear layer without an activation function. Okay, so we just remove the sigmoid activation function. Okay? So the demo I've already shown you. Okay, next important result is the expressivity of this neural network is actually very large. And actually, you can show mathematically that you can instantiate multi-layer perceptron even with just one hidden layer to approximate to arbitrary precision any function that you give me. So give me one function, I will tell you there exists an MLP of this kind which can approximate this function arbitrarily well. Okay? By just doing that. So you can have something very complicated or that looks complicated, like, I don't know, if this is x, f of x, the function we are trying to approximate, and f of x is maybe something like this. Okay, what I'm saying is that there exist actually several neural networks of this kind which can approximate this to arbitrary precision. Do you believe me? I mean, how could I approximate something like this from these simple binary classifiers? And that works in 1D, but also in any number of dimensions, by the way. Any guess? So the demonstration is quite easy if we consider even a simpler version of the MLP of this kind, where I would define my neural network output as just an MLP with one single layer, okay, such that the output, and and I can do that with the sine or the sigmoid, it does not really matter actually. And then you sum over this, Wi. Okay, so with this architecture, what I'm saying is basically I have something like this. I have X, then I'm mapping this to this quantity, which is sine of X plus B, meaning that actually this box is connected to the others using weights that are set to 1. Okay, if I have only actually, just maybe to simplify further, if I have only one input, I have something like this. Sorry. So this one is connected like this, with a weight which is equal to 1. I have an offset which is specific to each element. Okay, and then I would be summing all these values with weights, this one, the Wi. Okay? So one hidden layer, I'm setting everything in the first linear layer is just the identity, okay, but with some offset, and then the last is just a linear projection. Okay? And with this simple neural network, I can approximate any function like that. Okay, how can we do that? So the trick is to build an approximation step by step. So in this series of figures, what you will see is the sequential construction of this model, in which the dash thread 1 corresponds to the previous approximation, which will just try to improve, okay, by adding one more unit of this kind. Okay, and the unit that we'll add, I will show it in blue. Okay, and the sum of the two will produce the new version of the model. Okay, which will be shown by the plain red line. Okay, so initially I'm assuming that my model is just 0 everywhere. Okay, and I will try to improve my model such that it makes a correct prediction at least for this point. Okay, so I want the model, because the function in black that I'm trying to approximate at -5 is equal to, I don't know, something above 1. Okay, I want at least my model, my neural network, to be correct at this position. Okay, the way I could do that would be by adding to my constant model this increment. Okay, and this increment is just this sign translated exactly at the correct position, and then rescaled by the right amount to predict the correct value. Okay? So now my red model, is still very poor, but at least it's making a correct prediction there. Okay? And now what I will do is that I will try to improve this model such that it makes a correct prediction for some position a bit to the right of that point. How can I do that? So my previous model is the one with the red dashes. I want to make a correct prediction here. Okay, so the way I would be doing that would be by adding a new element to my sum. The new element that I can add is the one in blue. When you sum the dashed red with the dashed blue, you get the plain blue. And now you see that this model is making two correct predictions, one there at the previous point and one there at the new point. Okay, and the only thing I'm doing is to add these units. I'm just shifting them one point after the other and rescaling their outputs such that it's making the correct prediction. And I can repeat that for all the next positions that I want. Okay, and now I have a red model, which is an approximation of the black curve. Okay, then you could tell me, but actually it's not very good. There are many. It's only approximating very crudely the black line, but I suppose you can quickly imagine that I can go to arbitrary precisions by just discretizing further and further my red model. Okay, that's it. So this result is actually very powerful, and you can show mathematically this important theorem, which we call the universal approximation theorem, which is a theorem which was already known back at the end of the 80s, which basically says that give me any function on some p-dimensional hypercube, then there exists some function of this kind, okay, in which you should recognize that this is nothing else than a one hidden layer MLP. There exists any function f such that this function f approximates to some arbitrary precision epsilon the target function lowercase f. So this actually is very powerful because we knew already 40 years ago or so that these neural networks actually they can approximate any function. And this theorem shows that indeed that's true. However, this theorem does not tell us how we should find f. So this has been very frustrating for the community because we knew about the existence of these powerful functions, but we could not find them. Okay, we didn't know at the time algorithms to identify this, the parameters that we should associate to the MLP. Okay, so let's see how we can do that. So how do we train this neural network? Okay, so the first thing that we need is a loss function. And the loss function will depend on the task that we want to solve, or equivalently to the assumptions that we are making about the conditional probability distribution of the output given the input. And usually that's the philosophy I will follow. Start by just specifying your conditional of the output given the input, then do maximal likelihood estimation, and from there will result the loss that you should minimize. We have already done that today in the case of binary classification. We arrive to the binary cross-entropy loss. You can do the same if you have a multi-class classification problem, in which case you would so in this case you would assume a categorical likelihood, a categorical distribution for y given x, but then you arrive to something equivalent, which is the cross-entropy loss again, not the binary but the multi-class cross-entropy loss, which takes this form. Okay, and similarly for regression, you could start from the assumption that py given x follows, for example, a Gaussian distribution, then you do maximal likelihood estimation, and you arrive eventually to the problem of minimizing the squared error between the target and your output. Okay? Okay, so now that we have the losses, and actually it's a good exercise if you try to rederive this yourself, but just start from the assumption of a Gaussian, do maximum likelihood estimation, and in 2 or 3 lines, everything simplifies back to the sum of squared error. Okay, so we assume that we know the loss that we want to minimize. Now the question is, how do we minimize this loss with respect to the parameters, for example, of the neural network that we consider? So first of all, maybe to clarify, if this is the neural network that we consider to solve some binary classification problem or regression problem, can you tell me what are the parameters actually of this architecture? So where do you see the parameters there? What are we trying to do? Yes. Yes. So the weights are these matrices that we have there. Okay, we have different ones. 1, 2, 3, L. Together with the vectors of offsets, so the B's. And okay, which means that the optimization problem that we want to solve can be very high dimensional. Okay, so these are matrices where the size, for example, of this matrix is the product of the dimension of the input vector and the dimension of the first layer. Okay, and then the dimension of this matrix is the product of these 2 dimensions, and so on and so forth. So this can grow very quickly to thousands, millions, or even billions of parameters. Okay? Okay, so how do we do that? How do we optimize the parameters in deep learning? The main algorithm that we use is called gradient descent. So unfortunately, the loss functions that we consider, they don't have a closed form solution. So the only thing we can do is to resort to an approximation, to numerical optimization algorithm, which usually don't come with any guarantee with respect to the quality of the solution that we will obtain. Okay? And in gradient descent, and even worse in deep learning, you will see that we will be very satisfied with very poor approximation of the solution. Okay, so how do we do that? So let's say in black, you have the loss that we want to minimize. Okay, and that's a function that we can evaluate everywhere. Okay, but because it's so high dimensional, we can't determine in one go where is the minimum of that function. Okay, so what do we do instead? Well, we just say that, okay, so let's say the current parameterization of the parameter is the blue point. Okay, we fix the values of W and B to something. And then we'll try to improve this parameter such that the loss is slightly smaller than what it currently is. Okay? And the way we would be doing that would be by considering a first order approximation around the current parameterization theta 0. Okay? So we consider a surrogate of the loss, and the surrogate, I will call it L hat. Okay? It's shown here in red. And I'm defining this surrogate as the value of the loss itself at theta 0, the current parameters, plus this linear term. Okay, I'm just considering the gradient of the loss with respect to the parameters. I'm saying in the immediate neighborhood of theta 0, it's as if I had an hyperplane defined by this gradient. Okay, I consider it flat, basically, and following the gradient, okay, which you see there with this dashed black line. But of course, I'm not crazy. I'm not saying the function or the function is flat everywhere. What I'm saying is that if I'm going too far from theta 0, then I should be penalized, okay, because I'm basically saying that my linear approximation is correct only in the immediate neighborhood of theta 0. And I'm saying that by adding this penalty, this quadratic penalty, so 1 over 2 sigma of the norm, the square norm of epsilon. Okay? And basically, when you compute this, you will get something like this. We'll get a parabola, which corresponds to our surrogate. Now, how do you minimize the parabola? Well, a parabola is a convex function, so you can just look for the values of the parabola for which the gradient of the parabola is equal to 0, and you will get the position of the minimum of the parabola. Okay, so if you do that, this parabola can be minimized in closed form, and in this case, the minimizer of the approximation will be such that the gradient of the surrogate of the approximation is equal to 0. Okay, and when now you differentiate L hat with respect to epsilon, okay, when you differentiate this expression with respect to epsilon, this cancels, then you have just the gradient of the loss, and then you have the gradient of this term, and you have something like this. So you have the gradient plus 1 over gamma times epsilon. Okay? Now, yes? Because so in this case, we make sure this is a convex function. Okay, so this is a convex function, not a concave function. No? You have a positive epsilon there, so it can only go up. If you add instead a minus there, you would get a concave function. Okay, so you solve, and then, so when you solve this equation with respect to epsilon, well, you get that epsilon should be equal to minus gamma times the gradient of the loss. Okay, so that means now, if I'm currently at this position in blue, I can find a supposedly better configuration of the parameters by jumping to the red point, okay, which is given by following the solution of that problem. Okay, so by doing a step in the opposite direction of the gradient with an amplitude of gamma. Okay, and that gives us the main update rule of gradient descent, which says that, okay, to update your parameters from theta t to theta t plus 1, you just follow the opposite direction of the gradient of the loss evaluated at the current parameters, and you modulate this step by a factor gamma. Okay? So if we do that on this problem, this is what would happen. We get something like this. And eventually, it saturates, or the gradients are close to 0, and we are not making any changes anymore to theta t, in which case we stop. Any issue with that? Yes? Yes? Maybe? I want to minimize my training error. I want to do empirical risk minimization. So you are correct. There is no guarantee that the minimum or the solution we will find will correspond to the global minimum of the training loss. Okay, and indeed, if, for example, just on this simple problem, I had started just a bit to the right, then I would have obtained, by following the same update rule, another minimum. Okay, so that's already something very important. The initialization of this algorithm is very critical. If that will determine basically the quality by a lot, the quality of the final solution. What I've not mentioned yet really is what is the effect of gamma. So this term that I have here. Well, gamma so let's say we are currently there at the red points. What I'm saying is that I will consider an approximation of this loss, okay, using this kind of parabola. Okay? Which is L hat. Okay, but this is a function of the gamma value that I've set. If I set a value of gamma which is small or large, this will have an effect on the parabola. If gamma is large, that will result in a larger parabola. If gamma is very small, that will result in something like this. Okay? Which means, with respect to the update rule that we've derived, since we follow a step which is modulated by the amplitude of gamma, okay, if we have gamma which is large, we'll be jumping, for example, to this position in one go. So that would be theta t plus 1. On the other hand, if I had considered this smaller gamma, I would have made a jump only there. Okay? So the gamma is what we also call the learning rate. It's basically how far we allow the update of the parameter to change. Okay, so this is an example of what we would have obtained, for example, with a large learning rate, with a large value of gamma. You see that the parabola is much larger than before. Okay, in this case, because it's large, also it's leading to some numerical problems, which in this case is the divergence. So, for example, in this case, we would be jumping from the blue to the other side of the function. And then we repeat this, and we may be we may be oscillating for quite a while before reaching maybe the minimum, or what could also happen is that we actually escape and fall back to some other part of the function. Okay, so that does not seem like a very good algorithm. It's sensitive to the initialization. It's sensitive to the gamma value that we use. And actually, it's even worse in terms of the complexity of this algorithm, because what we need is to compute the gradient at every step. We need to differentiate the loss with respect to the parameters at every step. And this loss, okay, if we say that we are doing empirical risk minimization, it's just the empirical mean of the loss values for all the inputs and outputs of our training set. Okay? So if this is our loss, then that means the gradient of the loss will be the gradient of the sum, which I can rewrite as the sum of the gradients of the loss evaluated at each input-output pair. Okay? So far, you should all agree with that, and you should also then agree that the computation of the loss, in terms of its time complexity, will be at least proportional to the number of elements in the training set. Okay, so if we have 10 elements, 10 input-output pairs, that's not a big cost, but as what you will have usually in deep learning, where your training set is of the size of several millions or more, then that means we'll have to iterate over the entire large training set at every step. This is too big, okay? Okay, what can we do to try to reduce this time complexity then? Yes. Okay, and which ones? Okay. Okay. Okay, that's a good idea. What do you think, all the others? Is that a good idea? Will we obtain good gradients if we approximate this sum by just randomly picking a subset of it? Who said no? Yeah. But that's what we'll do, okay? In deep learning, we'll do that, okay? And the main reason is because actually we don't care about this loss in the first place. We don't care about minimizing the training error very well. That's not our goal. That's only a proxy. The actual goal is to minimize the expected risk, not the empirical risk. We want to minimize the test error, not the training error, okay? Because we know quite well that if we minimize the training error too well, we are likely to overfit the data anyway. So we don't care about the exact solution. Okay, so that's the main argument. Since the empirical risk is already an approximation of the expected risk, it's actually not necessary to find the exact solution to that problem, because that's not the one we care about really. Okay, so let's not waste computation trying to estimate these gradients as accurately as possible. And so what we do instead in deep learning is what we call stochastic gradient descent, in which we'll select a random subset of the training elements, and we can push this idea to the extreme, and what we'll do at every step is to only pick one element of the training set. And we'll compute the loss on this single input-output pair, and then follow the opposite direction of the gradient for that pair. Okay? If you do that, we arrive to this expression for the update rule. Okay, so it's the same as before. To update the parameters from theta t to theta t plus 1, we follow the opposite direction of the gradient, but now not of the entire loss, of the loss evaluated only at a random pair of input and output from the training set. Okay, and again, we modulate this gradient by a learning rate. And if we do that, then of course now the time complexity of the update becomes independent with the size of the training set n. Okay, but that seems even worse. So now we have an algorithm which is sensitive to the initial position of the initial conditions of the parameters, which is sensitive to the learning rate, and which is actually acting randomly. How is that a good algorithm? So basically what I'm advocating for is, instead of following this kind of updates using gradient descent or batch gradient descent, we'll use this kind of drunken version of gradient descent, in which we'll just make almost random moves at every step. Okay, am I crazy or not? Mm-hmm. Yes, yes. So that's an important point. Each step is inexpensive in a sense. We don't need to think for very long in order to compute the step. Okay? And if I take again this analogy of being drunk, let's say you are at the end of a party and you want to come back to your place, but you are drunk. So you will not think very long for every step that you do to come back to your place, okay? Because you don't have the compute anymore to do that, okay? But you know that on average you will go towards the correct direction. You may be doing more steps than necessary, but on average the direction is correct, okay? That's the same analogy, okay? Instead of doing few steps very accurately, we'll be doing many more of them using very inexpensive calculations. Okay? And the reason we can do that is because we know that in expectation we'll be going in the correct direction. Okay? You are not completely doing these steps at random, you know more or less where to go. Okay? So mathematically, this is also what's going on. Actually, if you look at this update rule and you look at the average update or the expected update that we would make, then we would recover the update rule of batch gradient descent. If you consider this in expectation over all possible input-output pairs we could have drawn from the training set, then the average of this update is the same as the update of batch gradient descent. Okay? And so formally, this works because the gradient estimate, so this quantity can be used as an estimate of the gradient over the entire loss, okay? And it's a good estimate because it's an unbiased estimate, meaning if you look at the expected value of this estimate, we recover this quantity which corresponds to the gradient we wanted to follow in the first place. Okay, so the expected value of the gradient is the gradient of the entire loss. Of course, this comes with a price, which is the fact that the variance of this estimate, of course, is non-zero. Okay, and depending on whether or not this variance is large or not, that may lead to some issues, and actually in some other cases, this may also be beneficial. But we'll cover that later on. Okay, and then there is also an interesting other result, but which I will only mention, is that if you do pure stochastic gradient descent using updates using single elements at every step, and you only iterate once over your training set, then you can show that this algorithm is directly minimizing the expected risk, which is exactly what you want to do. Yes? Yes. Exactly. Yes. Yes. You use the input-output pairs only once, and then you just throw them away. Yes. You will see the first time you train a neural network, you just stop after one epoch, after one full iteration of your training set, and you will not have good results. Okay. If you had infinitely many data, that's what you should do. But usually you don't. Other questions? Okay, then let me finish maybe with this before the next break. What we can also show is that okay, so if you remember what we saw last week, we characterize the quality of the empirical risk minimizer using the bias variance decomposition and so on and so forth. And now what I'm saying is that we can go back a bit to this framework, but by considering also the fact that now we'll not be able to minimize the training error accurately. So we'll not be able to, if you remember the notations, we'll not be able to identify fd star, the minimizer of the training error, but we'll only have access to an approximation of it, f tilde of d star. Okay, and now that's the object that we should study. We should study if the expected discrepancy between the expected risk of this approximate minimizer to the base model is large or not. Okay, and there are results which show us that we can actually decompose this quantity in terms of 3 terms. The first term is the approximation error, which is due to the hypothesis space, okay, as before. Then we have the estimation error, which is due to the fact that we are minimizing the training error instead of minimizing directly the expected risk. And finally, we have this term, which considers the discrepancy between our approximation of the empirical risk minimizer and the expected risk of the empirical risk minimizer. Okay? And this last term is now due to the fact that we are using an approximate optimization algorithm. Okay, like stochastic gradient descent. And so this term is the optimization error due to the approximate optimization algorithm. And so now we have a trade-off between these 3 terms. And then there is this fundamental result by Léon Bottou and Olivier Bousquet from 10 years ago, which states that if you consider stochastic optimization algorithms like SGD and almost all others that we have in deep learning, they state that stochastic optimization algorithms will have strong generalization performance, okay, in terms of the excess error, in terms of this decomposition, despite being actually poor optimization algorithm for minimizing the empirical risk. Okay, so what does that say is that if you have a finite budget of computation, okay, the trade-off is actually, it may not be a good idea to try to minimize this quantity, the optimization error, okay, because the price you will have to pay, certainly if you minimize this too accurately, will be that this estimation error now will be very large. On the other hand, if you are only doing a poor job at minimizing the training error, okay, so this one is large, that may actually be beneficial because this can be reduced if you do that. Okay? Questions on this? Okay. Okay, then let's do a last break and we'll resume in, let's say, 10 minutes, 11:05. Okay, so before the break, I've given you an algorithm to identify good parameters of a neural network. Okay, and the algorithm we arrive to is stochastic gradient descent, in which what we do is that, okay, we say that we start from some position configuration theta t of the parameters, and then to update the next iterate, so theta t plus 1, we say that we just update theta t by following the opposite direction of the gradient. So you compute the gradient of the loss, modulated by some learning rate gamma. Okay? And this gradient can, and for example, in the case of stochastic gradient descent, can be approximated very crudely by just saying, for example, we'll consider the gradient of the loss between some output yi and the prediction of the neural network, so f of xi. Okay, and then we compare the two in the sense of the loss that we pick. We compute the gradient and we follow this opposite direction. Okay? Okay, next question, if that's the algorithm that we want to use, is but where do we get these gradients? How do we compute them in the first place? How do you get the gradients? So, for example, if that's the neural network we use and we are doing regression, that this output is just a real value, which we compare in the sense of the squared error, let's say, to some target that we know in the training set. How do we compute the gradient of that loss, let's say, with respect to this parameter W1? Okay, you can differentiate, but how? That's the question. Do you do that on paper? Okay, what's backpropagation? Yes? Okay, can you explain what you mean by backpropagate? Okay, and what do you do when you move backward? Of what? Yeah, but that's what we want to do. So what do you mean when you do that already for the last layer? If you want to compute the derivative of the loss with respect to W1, you say you go backward, you backpropagate, but what do you mean? Uh-huh. Actually, no, that's not correct. Yes? Yes? Yeah, so the trick will be to use the chain rule. And why I was saying this was not correct, what you said, is because we don't need to compute the derivative of the loss with respect to W1, we don't need the derivative of the loss with respect to WL. However, what we need is the derivative of the loss with respect to this quantity, the input itself, the argument. Okay, but not the W parameters. And then we'll be using the chain rule indeed. Okay, so let's see how to do that, but we'll actually have a whole lecture on this topic. So to minimize the loss in stochastic gradient descent, we need the gradient of the loss, okay, which is this vector of partial derivatives of the loss with respect to each one of the parameters. So this gradient is usually very large, okay? It's as large as the number of parameters we have in the network, meaning in the hundreds of millions, usually. Okay, but this vector, mathematically, just gathers the partial derivative for each one of the parameters, like each scalar parameter, theta k, okay? And what we are doing in deep learning is that we'll not be trying to deriving these gradients by hand analytically. We used to do that not too long ago, but since 2010 or so, we have now programs that we can use to directly compute exactly the gradients using the graph computation of the neural network. Okay? So this is what we do. The derivative will be evaluated automatically from that graph using automatic differentiation. And the core idea of automatic differentiation is to use the chain rule of differentiation, which says that, okay, the partial derivative of L with respect to some input theta t, theta I, okay, is the sum over the direct inputs of L. Okay, so L is a function of several arguments. Okay, these arguments, I will call them the parents of L when you look at the graph of computation. And for each of these arguments, what you do is that you compute the immediate partial derivative of L with respect to that argument times the partial derivative of that argument with respect to theta I. Okay, and then you sum all together. Okay, but you see, in order to do that, you need to compute another partial derivative. But this is just a recursive case. Okay, you can apply recursively the chain rule to recover this term. Okay, we'll see how to do that slowly next week. But this is really the principle we use in deep learning. Since we have defined a neural network as a composition of functions, okay, we've defined the logistic regression unit. This one, okay, is just a sum, a product, a sigmoid activation function. We can differentiate everything. So this expression is itself differentiable, okay, and we can differentiate through this expression by just using the chain rule, okay. And then we have said that, okay, but these layers, they are just the parallel compositions of this unit. So the layer composition is also differentiable, and the MLP is just another composition, but now of layers. And so if the layers are differentiable, their composition is also differentiable. Okay? So that's why we can do that. It's because everything is made of small functions that we can differentiate. Okay? So let's see one example. Let's say we have a very simple neural network made of one hidden layer. Okay, so we start from some input x, we make a linear projection, we have a sigmoid activation function, we make another projection to produce to produce one output. Then we take the sigmoid of that and we get a number which we can interpret as a probability value. Then we'll use as a loss the cross-entropy loss, okay, the one we have derived before. Maybe we'll consider that we have some regularization penalty just to make things a bit more interesting. Okay, this is just a way to complicate the loss. Okay, and then what we want now is to minimize this quantity L with respect to W1 and W2. Okay, but in order to do that, I need to have access to the gradients of the loss with respect to each one of these parameters. Okay, first, let's look at the corresponding graph of computation. So the main part is the part which you have below, which corresponds to the neural network itself. Okay, you have X multiplied with W, giving you some vector. You take the sigmoid, you apply the sigmoid activation function to each element. That gives you another vector, which you multiply further with another matrix. That gives you another vector, sigmoid, and then that produces some value y hat. This value y hat, then you compare it with some ground truth value y through some loss like the cross-entropy loss. Okay? But since in this loss I also have this term, okay, in which I also have the parameters. Okay, these parameters, they also contribute to this other part of the graph of computation, in which there you see the computation of the norm for the first and the second matrix. Then you sum these two norms, you multiply them with some regularization penalty lambda. That gives you a scalar, and now you have two scalars, the one from the cross-entropy loss below, and second, the one from the penalty. Then you sum this further, you sum these two values together, and that gives you the final loss, which we want to minimize. Okay? And now what I'm saying, in order to do that, I need access to the gradients of this node with respect to the red ones. Okay? And if we apply the chain rule backward, okay, then I know that, for example, the partial derivative of L with respect to W1 is what? Is the sum over the parents of L. What are the parents of L? It's U8 and U4. Okay. And then for each of them, what do? I compute the immediate partial derivative of L with respect to the first argument, U8, then multiply it with the partial derivative of U8 with respect to the parameter. Okay. And similarly for the other argument, you compute the partial derivative of U4, the second argument, times the partial derivative of U4 with respect to the parameters W1. Okay. And then you proceed recursively to compute, to evaluate this term, the partial derivative of U8 with respect to W1, and the partial derivative of U4 with respect to W1. So for example, the partial derivative of U8 with respect to W1, well, now you iterate over the parents of U8, U7 and lambda, and for each you compute the partial derivative of U8 with respect to each of them times the partial derivative of that argument with respect to W1. Okay, and you obtain, then you can unfold this expression recursively, starting from the outputs back to the parameters. Okay? Okay, what is interesting maybe for now is just to consider the part below, which correspond to the neural network. Okay. So when we go from the inputs to the outputs, okay, we don't consider the loss around these predictions. And you see that in order to compute the gradients, we need actually intermediate quantities. If you want to compute the gradients backward, okay, we'll need to know all these intermediate quantities, U1, U2, U3, and so on and so forth. Okay, why is that? If you look, for example, at the partial derivative of the output with respect to the first parameter, then if you apply the base rule, the chain rule, the partial derivative of y hat with respect to W1 is the partial derivative of y hat with respect to its parents. In this case, there is only one, so U3, times the partial derivative of U3 with respect to W1, which we further expand recursively by saying that this is just the same as the partial derivative of U3 with respect to its parent U2, and so on and so forth, times the partial derivative of U2 with respect to U1, times the partial derivative of U1 with respect to W1. Okay? And now with this product of partial derivatives, and in order to be able to evaluate them, we need to know these intermediate quantities. So for example, the partial derivative of y hat with respect to U3, if y hat let me do it here. So if we say y hat is equal to this, okay, then when we compute this, okay, we have to differentiate the sigmoid activation function and then to evaluate the derivative at U3. Okay, so we need to have remembered these intermediate quantities. And so this is what we do usually in deep learning. We'll have first a forward pass in which we evaluate forward the neural network going from inputs to outputs. Okay, and we could just remember the last value, the output. Okay, but if we are at the same time training this neural network, then we know that actually we'll have to remember all these intermediate values because they will be needed when we'll have to compute the gradients, which happens in the backward pass when we go from outputs to inputs. Okay? All right. Okay. So it seems that actually there is nothing mysterious in these neural networks. And how come it's only since 2010 or so that we are able to train these architectures? If before that time you were trying to train deep, and when I say deep, it's not very deep, just maybe 3, 4, 5 layers deep neural networks, actually very few people could manage to do that. It was very difficult to basically find good parameters value and to reach good results. And there is actually a fundamental obstacle to everything that I've presented so far, which is due to the architecture. Okay? And actually, when you study, if you take like this get a 5-layer MLP, 5-layer neural network, using sigmoid activation functions exactly as we have seen before, then what you would notice, if you look at the values of the gradients with respect to the parameters that appear early or close to the inputs or close to the output, what you would observe is that for the parameters, for example, in layer 1, the first layer, the gradients of these parameters, they are concentrated around 0. But as you go deeper, the gradients, so from layer 2, 3, 4, and 5, they eventually cover a wider range, okay, which is what we want, okay, because if this is really what's happening, it means that the gradients for layer 1 will be close to 0. So these updates there, this update for the parameters of layer 1, because this quantity is small, this update will be very small as well. So much that if you have many layers, the amplitude of the gradients actually tends to vanish to 0, and you are actually not able to train these first layers. Okay? So for very long, this is what we noticed. It seems very complicated to train these layers. As long as you have a few of them, it seems almost impossible to use gradient descent to tune these parameters. Okay, let's see what's going on. If we consider a 2 hidden layer MLP, where everything is scalar, so not even vectors, so we have scalar input vector layers of size 1, and we produce one output. Okay, so we just multiply some scalar with x, do a sigmoid activation, multiply with another scalar, produce another, then feed that through another sigmoid, multiply again, and finally we produce the output. Okay. If we implement this on a computer, this is the sequence of operations which would happen in the forward pass. So we would first compute this product that would produce the first intermediate value, U1, which we would pass through the sigmoid activation function that would produce another intermediate quantity, U2, and so on and so forth until we arrive to the output y hat. Okay, and then let's see what is the gradient of this output with respect to the very first parameter, the closest to the input. Well, we can again apply the chain rule, and the chain rule will tell us that the derivative of the output with respect to W1 can be unfolded as a big product of partial derivatives, okay, where we have the partial derivative of y hat with respect to its input, and recursively until we arrive to the partial derivative of u1 with respect to that parameter w1. Okay, each one of these partial derivatives, they are easy to compute. You just need to know how to differentiate one of these primitive operations, like a sum, like a product, and then we are composing this derivative using the chain rule. Okay, so here we would have the partial derivative of y hat given u5, the partial derivative of, so that means the partial derivative of the sigmoid activation with respect to u5. Then the second term in this product is the partial derivative of this product with respect to u4, so that gives us just the coefficient, the parameter w3. Then we have the sigmoid of the second layer. We have the same partial derivative of the sigmoid with respect to its argument, times then now the second parameter w2, times the partial derivative again of the sigmoid now, but for the first layer, times x, where here we have this partial derivative of u1 with respect to not w, but with respect to, with respect to, with respect to w, so that gives us x and not the parameter. Okay? So why is this interesting to look at? Is because what I'm saying is that these gradients, for the parameters close to the input, they will tend to vanish to 0. Okay? And this is something that you can see from this expression. Okay, do you see the gradients vanishing to 0? Okay. If I'm telling you that the partial derivative of the sigmoid activation function is like this, so the partial derivative, or the derivative of the sigmoid is a function bounded between 0 and 0.25 for any value. So wherever you evaluate this partial derivative, you get a number between 0 and 0.25. Okay? Which means that this number is necessarily smaller than 1/4, this one 2, and this one 2. And when you multiply many numbers, as many as you have layers in your neural network, and all of them are bounded between 0 and something smaller than 1, then their product will vanish exponentially fast to 0. Okay, so that's why the gradients are vanishing if you use an MLP. As you make the neural network deeper, the more the gradients will vanish, and that problem will be more serious for the layers, the first layer, than of course for the last layers. Yes? Okay, because the algorithm that we use to optimize the parameter is this one. Okay, so, and when I said we use stochastic gradient descent, we start from a random guess, random initialization of the parameter. And then we make a step in the opposite direction of the gradient. Okay? But now this gradient is 0. So I'm just not moving. Yeah, but only those ones. Which means that you will not be able to instantiate very big networks because you will not be able to train them. Okay? Okay, so how do we fix this problem? Yes. Yeah. Okay, so it's exactly that. So the issue. Okay, so this is the sigmoid activation function, and you see that the gradient of this function will be 0 there because the function is flat, will be 0 there because it's flat, and at most will be positive, but at most equal to 0.25 in this regime. So what we need instead is to replace this activation function with a function such that the gradient will not be bounded like it's the case for the sigmoid activation function. Okay, and one simple way to do that is to say, instead of using the sigmoid activation function, we will use a function which is negative for any negative x, which is equal to 0 for any negative value, any negative input. Otherwise, is equal to the input. Okay, and this is what we call the rectified linear unit, or ReLU, which we can define simply as the max between 0 and x. Okay, so if x is negative, then the max between this is 0, so we output a 0 value. Otherwise, if it's positive, then the max is x, and in this case, we just replicate x at the output. And why is this convenient? Well, because now the gradient of this ReLU is either 0 in the negative regime, but will be 1 for all the positive values. Which means that when we have this product of partial derivatives, we'll no longer have these quantities being bounded between smaller than 1, but instead they will be exactly equal to 1. Okay, so this is what we have. Okay, we have something like this now. And if you replace these activation functions, indeed, you go from sigmoid to ReLU, then suddenly it becomes so much easier to train these neural networks. Okay, that I will skip. What is also important for you, and I will just show you that with the demo just afterwards, is that there are many other choices of activation functions. So you already know two of them now, the sigmoid activation function and the ReLU, but there are dozens of papers just proposing activation functions and arguing that, yes, really this one is really better than the others. And I've shown you a few of them there. It's indeed true that that will matter depending on the architecture, but it's not really important yet. What you should remember from today at least is that one of the main reasons of switching from sigmoid to ReLU is to prevent this saturation regime of the activation functions, which lead to vanishing gradients. And if you have vanishing gradients, then you cannot train your architecture. Okay, let me switch. Up. Where am I? Okay. Okay, so now for the last part, I just want to show you an example, a concrete example in code of one of these multi-layer perceptron, and we'll try to evaluate whether or not they actually work to solve a simple problem. Okay, so the data I will use is this one. Yep. Okay, so I will be setting a classification problem where the goal will be from a 2D coordinate of a point to tell whether this point comes from the yellow class or from the black class. Okay? That seems easy, right? Okay, so let's see first with a linear model. And I will just, so that we can. So I will instantiate a linear model as a degenerate neural network in which I'm just chaining one layer, and in this case, one linear layer that goes from the dimension D of the data to the number of classes, in this case 2. Okay, that's it. Then I will use the cross-entropy loss. I will use a numerical optimizer, which is called Adam. Okay, basically, it's just a variation of stochastic gradient descent, but we'll study that next week. And then I have this training loop in which at each iteration, I do a forward pass. So I just evaluate my input data through my model. That gives me the prediction, okay, the output of the linear model in this case. Then I evaluate my predictions and I compare them against the ground truth, the y, through some criterion, which in this case is my cross-entropy loss. Okay, everything. Then this is completely irrelevant. This is just for evaluating the accuracy and plotting stuff in the console. And then these three steps correspond to the computation of the gradients. So optimizer.0grad will basically reset all the gradients to 0. Okay, and then when you do backward call, you basically do a backward pass through the graph of computation, which is being built for you implicitly. Okay, but it's being remembered, and actually when this is happening there, when we compute the predictions, the graph of computation is being built as the expression is being evaluated and stored, such that when we come back and do a backward, okay, then we can reuse this graph and follow it to apply the chain rule backward. So the backward will compute all these gradients, and once we've computed the gradients, then we can actually use them to make a step using the optimizer. Okay? So this recipe will remain more or less the same even at the end of the course. It's more or less always like this. you instantiate a neural network, you have this training loop where you iterate over your data set, you have some loss, and you make steps. Does it work? Okay, let's try again then. Does it work? Will it work? Okay, no, of course, it's a linear model. The data is obviously non-linearly separable. There is no single line we could trace to separate the yellow from the blue. Okay, so we'll arrive to a trade-off, to a compromise, and in this case, the best trade-off, so the best configuration of this hyperplane gives us this. Okay, where indeed we have more yellow stuff classified as yellow than for this region. It's the best way we could put the hyperplane, and vice versa for the other class. Okay? Okay, so now we'll reuse exactly the same code. Let me just... Okay, so same code as before, same linear model, just to show you I'm not cheating. Okay, everything else is the same, and I get the same kind of hyperplane. Okay? All right. So this linear function, I can explode it into two linear operators. If you, do you all agree that if I multiply a vector with a matrix, I could say that this matrix is itself the result of the multiplication of two matrices together. Okay, so nothing prevents me from linearly projecting my data from dimension 2 to h, like let's say 10 first, and then back linearly from 10 to c, from 10 to 2. Okay? And I'm not putting any non-linear activation function in between. Okay? So this should still be a linear operator, and supposedly the decision boundary should still be an hyperplane like before. Do you all agree with that? Is this what will happen? Yes. Have you noticed a difference? It's faster, okay? Actually, that may be counterintuitive, but when you reparameterize a matrix as a product of matrices, you have more parameters, but that simplifies a lot, actually, the optimization problem. And in this case, it converges faster. Okay, but that does not seem to work very well regardless. We still get this hyperplane, and we can't disentangle these two classes. Okay, let's see what's going on if the only change I'm making is to add a sigmoid activation in between these two linear projections. What will happen? Will it work? Can you raise your hand? It won't work. It will be as bad as before. Can you raise your hand? Okay, what about everyone else? Yes? Okay. Okay, I should have trained longer. Let me... Is it bad? It's just one layer. I just have one layer. Okay. I will show you that when I consider deeper networks. But here I'm doing I'm doing this. Directly. Okay. One change, and now it works. Okay. Then you may wonder what's the value of having shorter or larger layers. So I could, for example, set it to 100. And then I repeat. So let me maybe zoom out a bit. Okay, that works too. Okay, let's see what the kind of results we have now if we consider 1, 2, 3, 4, and 5 layer MLP with sigmoid activation functions. And I will set this back to 10. Okay, that seems a bit more difficult. So it's still learning because it, even though we have a 5-layer MLP with sigmoid activation functions, we have non-vanishing gradients for the layers close to the output. Okay, and at the beginning, since we can't update them, it's almost as if we had random projections, and then using these random projections, then we just fine-tune a shallow MLP instead. Let's see what we have. If the only thing I'm changing now is to replace the sigmoid with ReLU. Okay, you see these lines. So these are artifacts that are due to the activation functions. We didn't have something like this before. It was smooth because the sigmoid activation is smooth. But the ReLU now, there is this kink there which creates this discontinuity. And actually what will happen is that when you have an MLP where you have replaced the activation function with ReLU, it will basically divide the input space into regions in which you have a linear model. So it's not very nice. What would you do if you were not satisfied with this kind of weird decision boundaries to try to improve it? So maybe we could have a shallower neural network first. So if we go back, for example, to a one hidden layer MLP, we would get something like this. Okay, so that works. Let me also reduce that. But we still have this many these abrupt changes in the decision boundaries. So if we wanted to erase that or try to improve that, how could we do that? Can you make a guess? Yeah, maybe you could start mixing these activation functions, but simpler than that. We have seen that before that if we have, for example, 5 layers, we still have these weird kind of shapes. But what you could do instead of adding layers, is to make the layers larger. Okay, so if we increase the number of parameters, in a sense, by having larger layers, the intuition is usually that you will get something which overfits. That's completely wrong in deep learning. Okay, if I go from 10 to 100, we'll get something like this. It's actually smoother than before, so simpler. And if I add many more of them, let's say 1000, okay, so we can get back the smoothness by just considering very large layers. It's not actually smooth at all. If we were to zoom in on this, on the decision boundaries, it would be made of small linear segments. But if you zoom out, it appears as if it was smooth. Okay, questions? All right, so that's it for today then. See you next week. Thank you.